All right, guys. Good afternoon, everyone. I'd like to do a little bit of house cleaning before starting the lecture. So you guys, you know that today is what day is today? The 11th, 10th, something like that. So we're here. We're in this week, and look, there's midterm next week. So that's gonna be on Thursday, okay? And it's gonna be in class. It shouldn't take too long, and it's going to be mostly conceptual. You're going to need a calculator, probably just to calculate some easy numbers, but you shouldn't expect a lot of computation here. It's going to be mostly conceptual. Okay? Yes?
I have a question. So do we have a formula sheet, or do we make a cheat sheet for ourselves or something?
No cheat sheet, no formula sheet,
We have
no.
to memorize all the equations.
You don't have to memorize anything. I'm going to give you the equations. Okay. So I like, for example, equations in which I give you the equation and I tell you that you tell me what each term means. It's more about conceptual understanding, not about memorizing. Probably there might be some equations that I really want you to remember, but they just make sense. Like, for example, mean stress. Okay? So you should know how to calculate mean stress. Or the deviatoric stress tensor. It's not a formula, it's a concept. Okay, so things like that you should know. I'm going to check the last year exam to see if what I can share with you. But you'll be hearing from me soon. So next week, and also during this week, we're working on this Poro Elasticity project, and next week I'm going to ask you for the abstract. Okay, I'm going to send you some specific guidelines about the project that you're going to be working on, and if you have some questions about that, probably I think Tuesday will be a great time to discuss if you haven't decided yet what you're going to be working on. And I'll talk a little bit more about that. But remember that there's going to be the week of the exam without an assignment, without the project, but you're going to have to work on writing an abstract. So please, study for the exam. Again, it is mostly conceptual. It's not going to be hard. It's not going to be long. But you should know everything we have covered so far. Okay, so let's continue then with talking about poroelasticity. Okay, so last week we talked about the equations that define the poroelastic solid, which are the ones I have over here, 1, 2, and 3. And we also, based on some assumptions, we found what is the BO coefficient, what is the pore modulus, and how to measure that BO coefficient. Did you guys start working on the assignment? No? Some no? Usually it's not too difficult, okay? You just have to plot this data and you will find what is the BO modulus and the BO coefficient. Yes, John?
You had mentioned last class there was some influence of permeability on this. Or was it for a different portion?
We're going to get to that today, hopefully, okay?
Doesn't affect the line fitting at all.
Okay. Yeah, we didn't discuss about that yet, but that's we're gonna. I think we're gonna get to that today. Michael.
I just had one question on the homework. So, or in class, you just talk about confining pressure minus pore pressure.
Yes.
With BO coefficient.
Yes.
In the homework, you talk about it as mean stress versus minus pore pressure.
Yes.
Do you want us to include that vertical deviatoric stress and calculate the mean stress and
Yeah.
the correct pore pressure, or do you want us to do exactly what we have to know?
Good question. Actually, Chajin also was asking that. in the actual experiment that you have over here, your S1 is different than your S3.
Yeah.
So you're going to have S1, and here you're going to have S3. This equation over here and this variability, in order to get K, the only thing that you have to do is you have to evaluate the change in mean stress. So when you increase the confining pressure, you change simultaneously S1 and S3 the same amount. So when you take the changes of the mean stress, that is what is going to go in here. Here's going to be a change, and here there is going to be a change too.
Okay.
So even though if it's a state of stress which is not isotropic, we still can measure this isotropic constant as long as in the test we increase all of the stresses simultaneously and the same amount. Okay? Was that a question? Same question. Yeah. So in here, as long as you plot the mean stress, you will see that that's going to change the same in all directions. All right. So we saw how to calculate then the BO coefficient, and now we're going to see an application. We're going to start with the drain problem, and this is going to be the drain problem of reservoir depletion, a very common problem in reservoir geomechanics. In this case, we have a reservoir which is long and thin, and in which there is production going on, so that we lower the pore pressure. We further assume in this case that the reservoir is overlain by a more or less or a very tight cap rock, and also is underlain by another tight cap rock. Because this reservoir is going to be very thin and long, and we're going to assume that the cap rock is very compliant, we're going to would that be right-handed? So 1, 2, no, right? Let me fix that. So if I want 3, that was okay. No. One should be here, right? 2, 3. So 1, 2, 3. Okay. So that's going to be my coordinate system. I'm going to assume that the total stress over burden is going to be constant. And my objective is going to be to calculate the variation of horizontal stresses with decreasing pressure. Because of the geometry of the problem, I'm going to assume that after some time, the deformation of a section of the reservoir just happens in one direction, something that we have called the one-dimensional strain condition. And for this 1D strain condition, the vertical strain is going to be different than 0, but the horizontal strains are going to be 0. There is not going to be any change as we apply depletion. Let's try to solve now those variations of stresses with the new equations that we have developed. If you check your notes, we have written that here the effective stress is going to be equal to K, and in general to the stiffness matrix times the strain tensor. That's something that we already knew, right? But now we know that this effective stress tensor is actually the total stress tensor minus the BO coefficient times the pore pressure times the identity matrix is equal to C times the strain tensor, okay? And in this case, we're going to work with total stresses. You may say, why are we working in total stresses if effective stress is what is really making the rock deform? The problem in this case is it's very difficult, almost impossible to measure effective stresses in situ. You cannot measure that. You can measure total stresses. For example, if you wanted to predict overburden here, it would be the weight of everything on top. That's going to be the total stress. And if you wanted to measure horizontal stress in here, you would have to do a hydraulic fracture test. And a hydraulic fracture test is not going to measure effective stress, but it's going to measure total stress. Because if you were to do a hydraulic fracture somewhere over here, you will open everything around. You will push rocks, you will push fluids, you will push everything. So such a test with hydraulic fracture, which is vertical, will allow you to determine what is S22. In this case, S22 will be the minimum principal stress. Okay? Do not confuse that with S2. S22 is not the same as S2. So because of that, we're going to work in terms of total stresses. We want to understand what are the variations in terms of total stress. So let me modify a little bit this equation, which is the same as that one, and write the strain tensor as a function of the compliance matrix. And now let me write that in matrix form. With the Boyd notation, where I'm going to have epsilon 11, epsilon 22, epsilon 33, 2 times epsilon 23, 2 times up, 2 times epsilon 13, 2 times epsilon 12. This is something you already know. And here I'm going to make an assumption. Okay? You could make a different assumption here, and you could solve a more general type of solution, but I'm going to solve the easiest one. If you feel like making some derivations at home, probably you can do assuming an isotropic porous medium. But here I'm going to assume an isotropic porous medium. So if you remember, here we just had the Young modulus. Here Poisson ratio divided Young modulus. Young modulus, Young modulus. Poisson ratio divided Young modulus is 0, 0, and 1 divided shear modulus. So the step to go from here to there is linear isotropic elasticity. And now notice, now we're going to do something new. Instead of writing sigma, I'm going to write S11 minus alpha pp, S22 minus alpha pp, S33 minus alpha pp. What about the shear terms? Are they going to be affected by pore pressure? No, right? So I just can write this, S23, S13, and S12. Notice that in this case, what stays constant is the overburden. And what changes is the pore pressure, right? So there is going to be a change in pore pressure that is going to affect these two. These two are our unknowns. So in order to apply the one-dimensional strain condition, we know that epsilon 33 is not going to be 0, but this one will be 0, and that one will be 0 as well. So knowing that, we can write the equations for those. So if I just write out of these multiplications the equations, and I'm going to further consider that in this problem it is laterally extensive in this direction, but it's also laterally extensive in this direction too. So if that's the case, there is not going to be strain in this direction, there is not going to be strain in that direction, and therefore out of here S22 and S11 are going to be the same. All right. So if that's the case, these two are going to be the same, right? And let's just write it in terms of let's say S22, because I'm interested in that one over there. Okay, so then I'm going to have epsilon 11, which is equal to 0. First equation is going to be 1 minus Poisson ratio divided Young modulus times S22 minus alpha pp minus Poisson ratio divided Young modulus S33 minus pore pressure times BO coefficient, right? And also from here, this equation is going to be exactly the same, right? There is going to be a minus Poisson ratio here. I'm not going to write that because it's the same equation, so I'm just going to go to the third equation, in which epsilon 33 is going to be equal to, let's see, now 2 times Poisson ratio, which are those two, times S22 minus alpha pp plus 1 over E S33 minus alpha pp. So my objective here is going to be to combine these two equations so that I get the effective horizontal stress as a function of the vertical stress. And for that, if you look at the equation on the top, I have here effective horizontal stress, effective vertical stress, right? And if I wanted just to isolate, so let's call this one and this one 2. From equation number 1, the effective horizontal stress is going to be equal to minus, if it goes to the other side, it's going to be positive. So it's going to be Poisson ratio divided 1 minus Poisson ratio, which comes from over there, S33 minus alpha pp. Is there anything new to what we have done so far?
You just substituted, substitute that for that.
But not much, right? We already knew that. We already knew this relationship. But now we're going to express it in terms of total stress. So this one was already known. But now we're going to write it in terms of pore pressure. So if I just want to write the total stress, S22, as a function of pore pressure and overburden, and let's see, I'm going to have an alpha, a positive alpha over here, right? So it's going to be this times S33 plus, it's going to be 1 minus this alpha pp. That's right? The math is correct? I think so, right?
Would it come out to just being, you add.
I'm moving this one
over
to the right.
So we're going to come out to be, so it would be 1 plus mu over 1 minus mu. So you could make that to 1 minus mu plus mu over 1 minus mu. So it come over to 1 over 1 minus mu.
But I wanted to write it in separate terms.
Oh yeah, no, just shouldn't the coefficient in front of alpha be simplified to 1 over 1 minus mu?
So this is going to be 1 minus nu, and this is 1 minus nu is going to be 1 minus 2
It would be
nu
minus 2 mu over 1 minus mu.
times alpha times pp, right? So now with this equation, we can do something very interesting. What we can do is we can take a derivative of S22 with respect to pp, because that's what we vary, right? So if we say, what is the change of horizontal stress with the variation of pore pressure under the condition that overburden is constant, which is what I have just written. Does overburden depend on pore pressure? No, right? So the only thing I have left is this coefficient, and that poroelastic coefficient is the one that is going to control the stress path of the total stress. And we're going to call that coefficient A. So let me tell you physically what that means. What this means is that if we were to plot what is called a total stress plot versus pore pressure, so this is pore pressure, here we have total stress, and let's say that we start in a given location with an initial vertical stress somewhere over here, and let's say that the horizontal stresses are lower than the vertical stress, and they start somewhere over here. What's going to happen when I decrease the pressure, according to our assumption so far? What's going to happen to vertical stress? It's going to stay constant. So we're not changing the weight of what is here on top, right? So that's going to still remain the same. Did I tell you guys I went to Midland 2 weekends ago? My friend's house is at 200 meters from a huge drilling pad and completion path. You can see the jack pumps and everything. It's like almost in the backyard. Even you drive through the neighborhood, and there are some blocks that there are no houses, but there is just a well there, which is pumping oil from the ground. So you could have one of these in your backyard, especially if you move to Midland, which is not bad, all right? So if you control that, and you know there are no leaks of anything, it's no problem to have one of those nearby. Okay, but you should avoid also subsidence, and we're going to get into this. If you have too much subsidence, then that may be problematic for your house. That happened, for example, in California, in Long Beach, with subsidence with greater than, I think it was something like 5 meters, 6 meters. It was huge. All right, okay, so let's come back over here. My point was that we're not changing S33 but by taking fluids out of the formation. So the vertical stress is going to remain constant. Notice that time goes in that direction, right? And horizontal stress is going to decrease. Total horizontal stress is going to decrease. And the rate at which it decreases, if this is equal to 1, is that slope A, that number that we calculated over there. So the ratio of horizontal stress with pore pressure is going to be that. It's going to be that slope A. And if we come back to the field, as you deplete, you could also measure horizontal stress. And actually, there are many measurements and many cases that have documented how this horizontal stress, total horizontal stress, decreases with time. Because that's a value that you can actually measure. So apparently now we know how to calculate that decrease in total horizontal stress. Remember that effective stress, though, is going to always increase. The total horizontal stress, because it has the pressure component, it decreases. But the effective stress is going to always increase. And we're going to plot that in a bit in terms of the Mohr circle. But before I go to that, I want to highlight something else from this plot. Do you think we could go forever on this elastic path? No? Why not? What would happen at some time? What is going to break? The rock, and how is it going to break?
You just said the effective stress increases.
In all directions. The pores may collapse. If you have the rock made out of, for example, of a sandstone, you could break the grains. So at some point over here, there is going to be something which is called a compression yield cap. If, for example, you were dealing with a hydraulic fracture completion, you may create such huge effective stresses that your propant may crash. And that there are cases of that too. Especially with unconventionals, you want to lower the pore pressure as much as possible, and sometimes those formations are very deep, so you can obtain a very large change in pore pressure. But if you do that too much, you're going to get into very compressed fractures, and also you may crash some propant. There is one more thing over here that it may happen, and probably it won't be super clear from this plot, but it's going to be clear in a second when we talk about Mohr circle. Somewhere over here, also there is going to be a shear failure limit. If this slope is too high, you may run into this line, which is the shear failure line. Notice that here we're increasing a lot what is called the stress anisotropy, the ratio between the maximum principal stress, effective stress, and the minimum effective principal stress. If you increase those too much, you may run into shear failure. And at that point, your stress path is going to get to somewhere over here, and then it's just going to follow the shear failure line. So whether you go into the compression yield cap or into shear failure, it will depend a lot on what is your initial path, which depends in turn on the elastic properties and poroelastic properties of the formation. So let's try to see, now that we know the implications of that, let's try to see what are the possible values of that coefficient A. So you see that we have two variables over there. One is the BO coefficient, and its maximum value is equal to 1. And the other one is going to be the Poisson ratio. What about if the Poisson ratio is equal to 0? What is going to be the coefficient A? And let's assume that the BO coefficient is equal to 1. So if BO coefficient is equal to 1 and Poisson ratio is equal to 0, the coefficient A is going to be 1. And everything in between is just going to be proportional to the BO coefficient. So it's going to be a linear relationship. So this is going to be for Poisson ratio equal to 0. And what does that mean? What does a Poisson ratio equal to 0 mean? That the rock is not going to expand as you put more vertical stress into it. And notice that may not be good, because if the rock is not expanding as you put more stress, that means that the rock has to take all the stress. It's not going to balance some stress by enlarging to the sides. If you let the rock enlarge to the sides, it's going to be able to resist more, because it's going to try to enlarge, but it's going to get some support from the sides. And as we know, rocks are stress-sensitive materials, so the more effective stress you have in the rock, the stronger it gets. But if it can expand, then it's going to have to take all the load, all the vertical stress, just with the internal strength of the rock. So in that case, A is going to be the maximum value, and it's going to be equal to 1. So that means any change of pore pressure that you do is going to transfer into a change of total stress and also into a change of effective horizontal stress. If this is equal to 0, no change in total horizontal stress, but there is going to be a change in the vertical stress. So this is equal to 1, but wait. Let me rephrase what I said, because I didn't see that you were happy. So if this one is equal to 1, the change in total stress is going to be equal to the change in pore pressure. But there is not going to be a change in effective horizontal stress. Effective horizontal stress is going to remain the same. Okay.